GANs, or Generative Adversarial Neural Networks, are basically two types of neural network layers pitted against each other in an adversarial structure to achieve optimal goals individually or one goal together. The best example is creating deepfakes and then detecting deepfakes. The generator layer takes input and applies random noise to it and sends the output to the discriminator. The discriminator matches the output to the original input and sends back variance. That is a sort of a simplistic view of what is happening, and GANs are far more complex, but you get the general idea. The generator uses the input to produce a similar but varied output. So let's say I use a generative layer to produce an image. The discriminator layer will analyze the output and return the variance, which is backpropagated into the generator. So let's say I scribble some lines on paper and hand it to you and tell you that it's a horse. You throw it back at me and tell me that it's just scribbles and a horse has legs. I regenerate the scribbles with legs and so on until you are having trouble criticizing my horse and I'm becoming a better artist, which will never happen. Humans have been using GAN methodologies since Grog threw a rock at Thor for getting too close to his cave. And now our AI are using them to throw rocks at us. And here you can see the use of convolutional and connected layers we discussed in the last section on CNN, but in this case for GANs. But you should know that GAN architectures can be used for non-visual images, as we discussed in the ChatGPT section. Okay, so we're basically pitting two neural nets against each other in an adversarial way using independent loss functions to optimize the result. We'll look at loss functions a bit later, as I mentioned, but any of you who stayed in math have seen them before. So if you think that GANs are only used for images, then you're missing the whole value of adversarial positions. They can be used to test, improve, innovate, identify, classify, etc., any sensory input and response, not just images. To move to the next level, or general AI, advanced AI builders need to stop thinking like humans and start thinking like human-machine hybrids. Now, we may not like that as humans, but it is what you are looking for in your AI talent pool. As you can see, we have already covered most of the structure of GANs in prior sections of this presentation, so you're seeing a more complete picture of AI systems. You now have a foundation to comprehend everything AI. It is important to recognize that neural nets are not perfect and often have a lack of balance that we humans are born with. Now, I've written about the use of information that lies just beyond our human perceptive frames of reference that we use to temper or tune our cognition. Without this, we humans make mistakes or do not optimize our response to stimuli or optimally achieve our goals. Most of these balance mechanisms are just starting to be developed in advanced AI. Neural nets suffer from a form of overfitting and stagnated learning when the math fails. As we will see in the labs, we use the slope of a derivative to adjust weights in a neural net, but as anyone who knows math can tell you, recurrent derivatives are prone to zero or infinity. This results in an effect called the vanishing gradient problem, which effectively freezes an AI with ultra small values for the weight updates. It basically stops learning or improving. We offset this with various methods, such as careful selection of activation functions, using data or gradient control, normalization, skipping layers, etc. All things covered in the Dev bootcamp. So once the GAN is complete, we can generate deepfakes and destroy the world. Or we can use these networks to better understand lies and deceit by using trained GAN discriminators as lie detectors. For now, they can be used to detect even ChatGPT output from human output using anomalous recognition methods because humans like me are deeply flawed. These human flaws are the secret sauce behind evolution, innovation, creativity, etc. You can think of guys like Steve Jobs or Elon Musk and their somewhat odd upbringings that motivated them to be who they are and so successful at innovation. Now, AIs do not evolve in this way. Instead, they leave a clear, distinct, and easily identifiable DNA trail for now. Okay, enough about GANs. Let's move on to RNNs. An RNN, or a recurrent neural network, processes flowing or sequential time-dependent or relevant data. They use the dimensionality of time as a ground truth, a temporal dependency. For example, words in a chat AI prompt that are earlier impact the words that are later in a sequential flow. This is simple human cascading, layering context. This is how attention or context is held in natural language processing chat AIs. RNNs are used in chat AI, image AI, generative music AI, trading in fintech artificial intelligence, and more recently in video translations and motion pathway analysis. RNNs persist data over changes in state due to subsequent data input. For example, holding context or attention over word inputs in a chat AI. You can see how a recurrent layer has been substituted in a CNN structure in place of the convolution layers, and this is what provides a foundation for holding state change variance over time using recurrent units or cells. Now, state change is immensely significant to artificial perception because it is vital to our own human perception. I have written about state change in humans and AI and its incredible value to our stimuli response mechanism, especially for improving response speed and lowering resource usage. It's why you as a human can respond to changes in context or real-world stimuli near instantly, because you have hundreds or thousands of years of evolution detecting state change in perception. RNNs carry state across time periods, updating as it goes by handing off the state to the next iteration, almost a bit like blockchain. So what's the difference between feed-forward neural net and an RNN? Well, feed-forward neural nets do not retain memory of prior layers like an RNN. Feed-forward neural nets move from input forward to the end output without prior layer dependency, while RNNs use each piece of data to update the previous state drawn from previous data. It persists and uses the prior state in a sort of an ongoing flow. Feed-forward neural nets process inputs separately, while RNNs process data sequentially with reference between the inputs. RNNs create loops and recurrences in the network. Feed-forward are unidirectional forward. Both have their benefits, with feed-forward neural nets being very efficient and RNNs being more robust. RNNs suffer from vanishing gradient, the memory erodes quickly. This is solved by advanced recurrent units like long short-term memory, persisting state using memory cells input controls, what input to update, part of all prior states and a current state as output, and forget gates, that's where it retains only some of the previous memory. So these are all the elements that they use. A GRU, or a gated recurrent unit, use an updated gate, how much of the hidden state to keep, and a reset gate, or how much of the new input to apply to the subsequent state. So RNNs persist and carry state for sequential dependent data processing. That's the real functionality and value in an RNN. Starting to lose my voice.